symmetry, right? The loading is symmetry, the geometry is symmetry. We can build one quarter of this model only. We do not have to worry about the whole model, and that is why you have this. In the handout, it's not very clear, but you can see what you have in your handout. This is 1/4 of that model. And we're going to use symmetry along this and this. We're going to use symmetry boundary condition and this at this edge and this edge. And the crack is at here. Loading is applied along this edge. Okay, this is a setup. We're going to build this model. The idea is because you have a crack here. Crack means free surface. Right? You do not have anything adhesion. You do not have any adhesion on the up surface, between the up surface and the bottom surface. So crack means a free surface. We're going to build two triangles, two rectangular shape, and then constrain this and constrain this using boundary condition and apply loading on the top edge. This is the setup. So the idea is to construct two triangles. First, two rectangular plates first. Structure, element.
Can you get a
And in your handout, you can see that we are choosing 183. 8 node, we're choosing this one. The more node you have, the more accurate result will be. So this one and this one, the difference is each element for this one is 4 nodes. Each element for this one will have 8 nodes. Okay? The more nodes you have, the more accurate the result will be. So we choose this one and close. And then material properties. Young modulus and Poisson solution.
Should get on Periscope.
Young modulus is, remember, is 1. Yeah, Young modulus is 1, Poisson solution is 0.3. And then we're going to create the geometry. Two rectangular plates, areas, rectangular by dimensions. And the dimension, the coordinate of these two is given. This is a first rectangular plate, and the crack will be here. So we're going to create another triangle, rectangular plate, different coordinates. Here and here, 2 plates, and they should be merged. These 2 areas are not connected; they should be merged. Okay? Otherwise, if you apply the loading in these 2 areas, it will be falling apart because you create these 2 areas separately. They are not a whole geometry yet, right? You should add them together. This is called Boolean's operation. You need to add these 2 areas. The reason that I didn't succeed for the previous ellipse because I created 4 lines, but I didn't add them together as a whole line, the loop. This right now you create 2 areas. If you do not add them together, you apply the loading, axis will not proceed because 2 geometries. Right now they are the same geometry. You only want to discretize into many small pieces of triangles. So I need to add these 2 geometries together. So-called operate Booleans add areas here and here, 2 areas. Okay, now the line in between disappear, the whole area. So you may ask him why bother? Why should I build these 2 areas first? I can build this whole area at the very beginning. Why bother two areas and then add them together? Because I want to have two segments along the bottom edge. From here to here is a crack. From here to here, I want to apply the symmetry boundary condition. Here I have a line. Here I have a line. I add these two areas together, but I have two lines in the bottom edge. Here and here. Okay? Because this segment and this segment will have different boundary condition. Okay? If you build the model, the whole area build the model from the very beginning, you will have only one line on the bottom edge. So this is the tricky part. Okay? So you need to have two lines, two segments along the bottom line. Otherwise, you cannot apply symmetry boundary condition on this segment and a crack on this segment. You cannot do that if it is a whole line. And then we can go to meshing tool. And in this meshing tool, we're not using smart meshing. We're not using automatically meshing tool, and we're controlling the mesh size to make the results more accurate. So meshing size control. That is meshing to a skip one step is here, size control, and the concentrated keep and create. You have a point here. This is a crack tip. Pick the crack tip, okay, and input. This is the key portion number 2, and you do not have to input anything here. You just click OK. I don't understand. Why create key points? Radius. The handout control reduce the radius. The default radius controlling is 3/4. So in the handout we use 1/4. And then 1 for the ratio. This is what is the meaning of the handout 6. Handout input 3 parameters. One is so-called radius of the fourth element. We're going to dense very fine mesh at here and coarse mesh away from the crack tip. This is how we are controlling the mesh. This is basically the meaning of these 3 parameters. Here, the mesh size will be very small, but away from the crack tip, the mesh size becomes larger and larger. Okay, this is what is the meaning of these 3 parameters. And you see the second row, this row, the ratio between the second row and the fourth row means the element size at this row and element size at this row, they have a ratio. Okay, you can control the ratio between the element size. And this is a controlling parameter when you are doing the meshing. And then we can mesh. Areas. 3. This is the result. You see? This is the crack tip. So nearby the crack tip, the mesh size is very small away from the crack tip is coarse. You do not have to use very dense mesh at here because stress concentration is at here. Okay? So, and then we can apply the boundary condition, symmetry boundary condition along this edge, symmetry about this plane, and symmetry about this plane, but symmetry boundary condition on the bottom edge is only applied on this segment, not including the crack. Symmetry about this plane basically means Uy on the segment, on the bottom segment will be 0. So we constrain Uy on the bottom edge from here to here. And then we constrain Ux on the left edge. It's also 0. This is the boundary condition. And then we apply the loading. It's pressure. And remember, it's distributed loading on the line, on this bottom line. But here we have two segments. From here to here, one segment. From here to here, the second segment. Both of them should be applied the loading, right? Why you have two segments on the top edge? Because you add two areas together. You didn't add those lines together. These two areas, you create these two areas. You add these two areas together to form a whole area, but those lines are still separated. That is why you have two segments, from here to here, from here to here. You should choose these two segments. Okay? Value is tensor loading, so it should be negative. Pressure is compressive. Right now it's a tensor loading, so it's tensor loading along y direction. You apply the loading, you apply the boundary condition, you can solve. When it's done, you can shoot the stress contour. We should have some stress concentration here, right? No matter what is sigma x, sigma yy, for me it's a stress, all of them at this crack tip should be very high. Why is a crack tip? Because there's a free surface here, right? From here to here, you do not apply any loading, you do not apply any constraint. This behaves like a crack, okay? So we can check stress concentration, stress distribution, contour, plot results, contour plot, nodal solution, stress along, maybe we can check XX component. You see? Here is red, here is blue. Why it is different in my computer? It's very strange. I have a very colorful picture on my screen, but here it's just like a black and red. I don't know why. This is you might in your computer you should see different picture than this. This is not good because the projector is not good. But on my screen you will see a very colorful picture. You will see the stress concentration at the crack tip. Basically you can zoom in.
Put it on the center.
You can zoom in the stress distribution at the crack tip. And this is how stress is distributed. When you have a crack, when you have a loading applied on the structure.
As soon as Mike comes over,
And next step is to plot the stress distribution along some direction. You have to define a path, and along that path you can plot
Mike loves
stress
cooking.
sigma x, sigma yy distribution along that path. So last time I already showed
I
that.
was like, well, I
Then
can
I'm going
invite
to
some
do
other
that
people.
again.
One of my friends is coming
You
into
need to
town.
do this in homework 2.
Just got back from like
And basically, you need to define a path.
Argentina or something. And then speaking of Mike, I invited Sarah. Invited this kid, but he won't be able to come till after his dance performance if he comes.
Gotcha.
I think that's it. You can invite whoever you want, just for free.
And I'm
Oh,
going to
and that
define
high
a path.
schoolers might be coming up too. And that high schooler, Keegan, might be coming up too. That was supposed to be in that those classes. I guess he takes a class here on
Define
Saturdays.
path and nodes. Because I want to be I want to plot the stress distribution along this x direction. I'm going to define a path. The starting point of this path is here. The ending point will be here. And each point will have a stress value, right? So I'm going to plot a curve. The horizontal axis will be the distance of any point away from this point. And the vertical axis of that curve will be the stress value at each point. So you will get a stress distribution along this direction. The curve basically will show that for you. So you define a path by nodes from here, 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 here. Right? This is the path you define. And give a name for the path. Any name. So, okay. And this basically this is the information of the path you defined. This is the first column is the name, and the second one is how many nodes on the path along the path. Okay. And then what kind of quantity you plot along the path? You have to do map onto the path. I want to plot stress along x direction. So just okay. Okay. And then plot. You define the path. You specify what quantity along the path. Now you can plot what is the curve will be like. Plot on graph Sx. Okay. This is the curve I want. In homework, the second question, you need to plot a curve. Show me like this. This is a distance away from the crack tip. This is a stress, sigma xx, away from the crack tip. It is cracked, right? Because at this point is the nearest point to the crack tip. So the stress value is highest. And when the distance becomes larger than the crack tip, the stress becoming smaller, eventually it goes to 0. It's not 0 yet, because it's not far away from this crack tip yet. You can define as long as possible. You can plot this curve. Basically, this is how ANSYS is used in engineering to show people what is the stress distribution. This is sigma xx. You can plot sigma yy, tau xy, and hormesis. So everyone got this? You got this? Okay, so if you got this, that means you can do homework 2. The second one, you shouldn't have any problems. Just plot this curve in your homework working sheet. And then you form the global stiffness matrix. Doing assembly, you use hand results. In ANSYS, we can do the same thing. If you geometry, how to discretize that geometry into small tetrahedrons, and how to apply the boundary condition. In the handout, we have a cylinder-shaped geometry. It's a steel cylinder, and we're going to build that in ANSYS. New structure. First step, the same thing with truss and beam, we choose elements. For 3D case, we should choose tetrahedral element, right? So go to solid, and here, quad means two-dimensional element. 4-node, 8-node, no matter it's 4-node or 8-node, is two-dimensional element. We're going to choose tetrahedral element, just scroll down. You will see a TET, T-E-T. You have tetrahedral 4-node, you have tetrahedral 10-node. In our introduction, we have 4-node tetrahedral. We choose this one, right? So this is the element we're going to have. Close. And second step is the material parameter. Linear, elastic, isotropic. This step is always the same. What is modulus? It's 3.7, and Poisson's ratio is 0.3. Okay, this is the materials properties, and then we're going to create the geometry. It's a cylinder. So how to create a cylinder? Again, you have many ways. In the handout, we just show one possibility. Okay, you have many different approach. We're going to build a rectangular shape, and we're going to resolve the rectangular shape along some axis, and we get a cylinder. Rotate the rectangle. So modeling, create area rectangular by 2 corners. What is the coordinate?
You're still watching. It says you're still watching.
What is the coordinate? 5061. And then we're going to, oops.
Do you think I didn't read that? I had my screen dark. Hold on.
This is not good.
What did you say?
Every time I have to delete this file log, otherwise I cannot use ANSYS. So
Yeah, that's crazy. That's the most important part, isn't it?
structure,
Next Friday?
and the type. We choose
I don't know what
tetrahedral,
that
solid,
means. I am a
tetrahedral 4-node. This is the element in our hand-calculated instruction. Okay, so 4-node element close. Then we input Young modulus and Poisson's
Thanks for
ratio.
the hearts, TC.
Structure, linear, elastic, isotropic. This one is
I cannot concentrate.
3. I remember this
It's
3,
like a list of everything.
right? 3.
Oh yeah, a lot of instructors
So
do
this
here.
is Young modulus
It's not
and
that
Poisson's
bad.
ratio, and then we create that area. Modeling, create
Everything that he's doing today is on this sheet of paper.
rectangular.
So we can do it whenever we want.
This one is 5. This one is 0. This one is 1.
Just tell him.
Create an area first. This is the area. It's not a solid. We need to create a solid. So we're going to do something. How to create a solid? I'm going to define an axis.
See him there?
The 5th step, your handout. We are going to define an axis, and then we're going to extrude this about that axis to form the three-dimensional geometry. Right now, its area is two-dimensional geometry. Right? You need to, if you are, this is the area. If you are going to extrude this area about this axis, it's like this.
Atrium, the native class.
You're going to get a geometry.
Open area.
Right? This is the
All the
axis.
walls
This is the
on
area.
right arm.
I'm going to extrude this area about this axis. This is the idea. Okay? So I'm going to define
So
an
you can
axis
write on
about
the
which axis I want to extrude this area. Basically, the fifth step in your handout is to define that axis.
I don't know. I don't know
So
where that jumped.
there's no,
I just found this the
in
other
fifth
day.
step in the handout is asking you to type something. It's not click. Okay? Type here. This is a command window. So this is the part. This is the thing that I'm going to introduce next time. This is APDL language. You can write some code. You can write some language, write some sentence
Did you hear
here,
that?
ANSYS will do the operation for you. Okay?
script.
This is the thing I'm going to introduce next time. After that, you do not have to use the menu. You just use the
APDL
command line
script or
to
something.
build your model.
Yeah.
So you just type,
Alright,
hey,
have fun, man. Peace out.
you see, when you type a key there, immediately ANSYS will pop up something for you. This is a reminder for you to type to what is the value for this, what is the argument for this case command.
Yeah,
So
it takes
K,
a little bit to understand his accent.
10, 0, 0, 0. The first number 10 is the index of that key point. And then you have three numbers, x, y, z. X, y, z means you are going to build a key point. The index of that key point is 10. And the coordinate of that key point is 0, 0, 0. Okay, this is the meaning of line. Okay, when you finish typing, you just enter. You will get a point at here. You see there's a 10 here. You build one key point in your geometry. Okay, and we can type another thing. We can build another. We can build another point because the objective is to build an axis. Right? We need 2 points to define your axis. So we need another point. And the index for that point is 11, and the coordinate, that one is x, y, z. When you finish typing the coordinate, enter. You see, we define another key point. Use these two commands. One is at here, one is at here. When you have 2 key points, you can define axis. Connect these 2 points, you form an axis. So we're going to use extrude. As I said, where is the extrude? Operate should be in operate. Extrude areas about axis. I'm going to extrude this area about this axis. Choose the area first. Okay. And the next step is asking you to choose the axis. Which axis? This axis. 2 points will define the axis for you. Okay. And how many? What is the? When you have area, when you have axis, you are going to extrude this area about axis. What is the degree? What is the degree you want to rotate this area? 90, 45, 90, 180, or 360. So that number basically is asking you what is the rotation angle. This area is rotating about that axis. What is the rotation angle? So we are building just 1/4 of that model, just 90 degrees. You get something like this. So it's very strange, right? But because you are looking at geometry in XY plane, you can tilt it. Right? This is the geometry. The idea, as I said, I build this area first. And then I extrude, I rotate this area about this axis along that direction. Rotate this area 90 degrees. I get this geometry, right? Just swipe through. This is how we get this cylinder. 3-dimensional geometry. This is how we build a very simple 3-dimensional geometry. If the geometry is more complicated, you will need advanced technique. We have many different approaches to build this. For example, you can build this top area first. and then extrude along this direction, right? Just swipe through along this direction. Or you can just build this circle, and then build another circle, and then use these two circles to form this area, and then extrude. So many different approaches. So this will depend on how creative we are building your model. Okay. The next step, as I said, the idea of the ANSYS is to use the stiffness method. We need to discretize this geometry into many small tetrahedral elements, right? So it's meshing. Meshing basically is discretize this geometry. I click meshing and mesh tool, and I just use freestyle smart size and click mesh. Doesn't matter much. This one doesn't matter much. You don't have to worry about the warning. So click this geometry. Okay. This is a discretized model. As I said, I discretize this geometry into many small pieces of tetrahedrals. Each small tetrahedral will have the stiffness matrix. In my previous lecture, I already give you the formulation for the stiffness matrix for each tetrahedral. Right now I have 100. For example, if I have 100 tetrahedral, I just form the global stiffness matrix, use the assembly procedure, I can solve it. Right? ANSYS will do that for you. You do not have to do the assembly, you do not have to solve it. This is basically how ANSYS works. But for each tetrahedral, it's derivation. People already input that stiffness matrix for each tetrahedral into ANSYS already. So that is why you can use ANSYS. And then we apply the boundary condition. Its condition on the loading on this geometry is you have an inner pressure. You have an inner pressure within the cylinder. And this symmetry along this area, because we only build 1/4 of the geometry, along this area should be symmetry, along that area should be symmetry. So we apply symmetry boundary condition here and there. And then we're going to apply our inner pressure in the inner surface. So that is the loading and boundary condition. And here, loading, define loads, apply structure, displacement, area. We're going to apply the symmetry boundary condition on this area, means UZ will be 0. Because the normal direction of this plane is along Z direction. Symmetry about this plane will be 0. Okay? So choose that area and choose UZ 0. This is a symmetry boundary condition for this area. Then you will see something in your screen. On the projector is not very clear. On your screen, you will see that something will show up when you successfully apply the symmetry boundary condition. And then we have another symmetry boundary condition to apply this area. This area, we have another area here, right? It's symmetry about this YZ plane. That means UX. The normal direction of that area is UX. So UX on that plane should be 0. UX, 0 is still here. So I apply two symmetry boundary conditions. And then, what is that? This one, area, and then click here. Yeah. You cannot see that area, but you can just click there. Yeah. So, and then pressure, inner pressure on the inner surface. So, pressure on area. This one. This is the inner surface of the cylinder, right? And then OK. Constant value, what is value? 1,000. It's 1,000. I remember it's 1,000. Doesn't matter much. This value is defined by different cases, right? I just input 1,000. So you will see something will show up. That means you successfully applied the inner pressure on the inner surface. And then we're going to solve it. Apply the boundary condition, apply the loading. We discretize the model already, so we can solve it. So you can make a guess. Which point should I have before I can solve it? Don't click on your screen. You can make a guess. Which point will have the highest tensile stress? Here or here? Or here or there? Which point will be red? Here? Inner pressure, this cylinder shape. Which point will be at the highest tensile stress? Which point will be at tension? Which point will be at compression? Just by common sense, just imagine. Do not solve it. You can see. You can imagine that. You have a cylinder. You have an inner pressure. The cylinder will be expanded, right? So this point will be at tensile loading. This point will be at compressive loading, right? This is the cylinder, and you apply an inner pressure within the cylinder. The whole cylinder will be expanding, right? And these 2 points will be at tensile loading, and these 2 points should be at compressive loading. So this one should be in red color, this one should be in blue color, if you look at the result. So I didn't solve it yet. I'm going to solve it. And then I'm going to plot the stress contour to see is that the case or not. Nodal solution, stress, XX. You see? On the projector, it's not that good. On your screen, you will see red color here, blue color here. That means red means positive value. Positive sigma XX means tensile stress along X direction. Negative value, blue means negative value, is compressive stress. You have a color bar here. This is a color bar. Blue is negative 800 something. Red means 1600 something. Positive, negative. Here is negative, here is positive. So basically this is how ANSYS works. Okay? We cannot solve this by hand because each small tetrahedral is already 12 by 12 matrix. We have so many small tetrahedrals, and form the global stiffness matrix and then solve it. It's not feasible. So I'm going to stop here. If you have questions on homework, you can come to me. I have the solution with me. So if you are okay with it, you are free to go. And